Welcome everyone to this next installment in the series where we're going through the fundamentals of machine learning. So today we're going to be talking about classification, which is a problem within supervised learning. So far we've been doing regression where we have some inputs, i.e. the number of rooms in a house, number of windows, etc., some features about a house, let's say, and we're trying to predict a continuous valued output, i.e. the price of the house or its age even. And there's another problem called classification, right? So what we do in this case is we have these features about a house, and our output is not continuous in nature, but it's discrete or binary. So we're trying to predict, for example, what age, like Victorian or Gregorian or etc. Or Georgian, is it? Yeah, that the house belongs to, or whether this house is suitable for students or not. So that's a binary question, and the first example that I gave was a categorical. So yeah, the simplest case is binary classification, and that's what we're going to be doing today. So yeah, let's get started. What we need, make sure you have this notebook up in front of you so you can go along live with me. So first off, let's just make some fake binary data. Okay, so this, to carry on this kind of example and just to make it clear in your head, let's say our x, our input, is the number of square meters or square miles, whatever a house has, and our output is we're trying to it's 1, right, if that house, let's say, is suitable for a family, and 0 if it's not, it's too small. So x, what I want you guys to do is sample x from a normal distribution. You don't have to, you can sample it from other distributions, but it's just simple. And y, our output, I want it to return 1 if it's above some arbitrary threshold that you guys decide, and 0 otherwise. Okay, so just a few minutes, go ahead, have a go at that, and I'm going to go through the answers right now. So yeah, this is quite simple, we've done it before. So np.random.rand n, and it takes one parameter, which is the number of samples we want, and I want m samples. Y, so I'm going to say y is equal to x is more than 0.5. okay, so when we do this, because this is a NumPy array, what happens is it does an element-wise more than operation on every element in this x vector, and for each element it returns as true or 1 if it's more than 0.5, and 0 or false if it's less than 0.5. okay, so that basically is like, yeah, if it's more than 0.5, we're going to say this is suitable for a family, this house, and if it's less than 0.5, we're going to say it's not. Okay, so this is what our sampled fake data looks like. Okay, so yeah, next step, let's build the model to fit this data. And our model is almost identical to what we use for linear regression. The only difference, and it's very small, is that we apply this sigmoid function to our outputs. And what the sigmoid does is squash our outputs, whatever values they may be. So z here can be, infinity to minus infinity, and what it will do is squash that output between 0 and 1, and that will represent a probability of it, being suitable for a family or not suitable for a family in this particular case. So yeah, we basically squash it between 0 and 1, so we can interpret this as a probability of it belonging to the positive class, which is the class where the value is 1 for that. which in this case is yes, it does. So this is yeah. So in this case, it's predicting the probability of it being suitable for a family. Okay. So yeah, you guys go ahead, pause this, have a few minutes to have a go at this. So here, just like before, we do a linear transformation. We define it. Here we apply that linear transformation, and then here we apply our sigmoid function to our outputs to squash them between 0 and 1. And you guys, yeah, you should be able to, well, you should kind of know how many inputs and outputs we have, right, based on what we've defined here. So yeah, pause it, have a go at that, and I'm going to go through the answer right now. Okay, so let's define our linear transformation. So I'm going to say self.linear layer is equal to torch.nn.linear. We've done this before. The number of inputs that I have is 1, which is, you know, the square mileage of the house. The number of outputs I have is 1, which is the probability that it's suitable for a family. So here I apply that linear transformation, so x is equal to self dot linear layer of x, and then here we just apply that sigmoid function. Luckily for us, you know, we don't actually have to write 1 over e to the minus x plus 1 because PyTorch has got this built in because, you know, it's used so often. So x is equal to f dot sigmoid of x. Cool. So the other part, other than this activation at the end, the other part that changes is our loss function. And what we use is binary cross entropy. Okay, so binary cross entropy, this cost, basically has 2 parts. Okay, so it has a left and the right side. And you see each part before it has this, so this one's multiplied by the label, this one's multiplied by 1 minus the label. And what that does is it kind of activates either the right half of the function or the left half of the function, depending on what the label is. So in the case that our label y is equal to 0, this term is multiplied by 0, so it just disappears, and we only end up with the right half of this equation. 1 minus our label, which in this case is 0, is just 1. So what our cost function ends up becoming when the label is equal to 0 is log of 1 minus our prediction. Okay, so this is what the log function looks like. And when we do log of 1 minus x, or in this case y hat, it turns into this curve here. So this curve has a very high value when y hat is equal to 1 and a value of 0 when y hat is equal to 0. So yeah, so that makes sense, because if our label is 0 then, and our y hat is 0, then yes, you know, our cost should be 0. But if our label is 0 and our y hat is 1, then our cost is basically infinite, because it's as wrong as it possibly can be, right? You predicted the total opposite of the label. So yeah, that's the right half. And let's consider if the label y equals 1. So what happens here? 1 minus y, 1 minus 1, 0 times this. So the right half disappears, and we end up with this left half, which, you know, because y equals 1, just becomes minus log y hat. And what that looks like is this. So when the label is 1 and our y hat is 1, our cost becomes 0. But when our label, so yeah, if our label is y, if our label is still 1 but our y hat is 0 now, the cost becomes infinite. And that's about it really. So basically, yeah, it just checks how far we are away from the label, and it either gives a 0, you know, a number between 0 or infinity, which is how wrong or right we are. So yeah, that's basically it. It's not too complicated. The only thing that you need to kind of be comfortable with is the fact that depending on the label, our cost function changes because we're either activating the left side or the right side of this equation. And yeah, that's about it. We don't and yeah, when we implement this, we actually don't need to, just like before, we just use f.sigmoid. We don't have to kind of write out this whole equation. PyTorch has built-in binary cross entropy cost function, which we can just use. Okay, so what I want you guys to do now, we're going to basically, we've defined our model. We know what our cost function is now. So let's, train that that model that we defined earlier to actually solve or fit the data that we have, the fake data. So first thing that I need you to do here, and you should pause it in a second, is convert x and y into tensors so that we can use them with our PyTorch model. And I also want you to add the batch dimension, as it's called, to these. Okay, so what this returns up here is just a vector which only has a single dimension, which is just of length 50. But PyTorch, when it's working with this data, it expects a matrix which is m by n, where m is the number of data points that we have and n is the number of features that we have. So we just kind of need to add that extra dimension so that our PyTorch model can work with it. Okay, and we define we basically instantiate our model here from the class that we defined. Same with the optimizer. And here, this is, apart from that line, this is what you guys need to complete. So using our model, make a prediction, compute the loss of that prediction, calculate the derivative of the loss with respect to our weights, take the optimization step, like update our weights using gradient, and then reset the stored gradients to 0. Okay, so this is our training loop. So complete that line, and the inside of our training loop. Just pause it right now, have a go, and I'm going to go through the answers now. Okay, so x is equal to torch.tensor x dot view minus 1 1. So we just add this extra dimension, which is 1, which is basically the number of features we have, and this will basically, because we have 50 data points. Do we have 50? Yeah, m by default is 50, so we have 50 data points. This will fit, to the 50. We do the same thing for y. Here we basically convert it to a double. So usually this is in the form of a float, which I believe is a 32-bit. Yeah, I believe it's a 32-bit decimal number, but double is a 64-bit decimal number. Well, basically, this, when I was actually trying to use this, it was giving me some error, basically telling me that y needs to be a double for it to work. So so that's why that's there. I don't know exactly the reason why PyTorch requires that, but it does, and I want this to work, so that's what I'm doing. Now we instantiate our our hypothesis, from the class that we defined above, and we also convert that into a double again because PyTorch said so. And then we define our optimizer. In this case, we're using the Adam optimizer, which is going to be optimizing the parameters of our hypothesis with the learning rate of 0.01. Okay, and this I just added in there so we can visualize our hypothesis before training, so that we can compare it to after we've trained it, and we can see what it looks like. Epochs, okay, 1,000 epochs, arbitrary, we can play around with that later. This is basically going to store the average cost per example for each epoch, so that we can plot our cost curve after. Okay, so for epoch and range epoch, so for every epoch we make this empty list, which is going to store the cost or the loss for each example in that particular epoch. Okay, and then here for xy and zip xy, we're iterating over each data point individually. So make prediction. My prediction is equal to h of x. My loss is equal to, and here we use PyTorch built-in binary cross entropy of our prediction and our y. Calculate the derivatives, so loss dot backward. Make the optimization step, optimizer dot step, and then finally reset the stored gradient, so optimizer dot 0 grad. And then yeah, we append the losses there, and then finally at the end of each epoch we basically get the average cost per example for that epoch, and we store it in this other list here. Okay, yeah, so let's run that. Cool, so this basically shows our hypothesis before training. As you can see, it's not very good, it doesn't make good predictions. And here we can see, yeah, our loss, keeps decreasing, and finally our model, our predictions basically align very closely with the ground truth. And I can train this for even more epochs or less, and we'll basically see how with different amounts of training what our hypothesis looks like. So I'll give that a second, it might take a while. I mean, yeah, if you guys have any questions about any of this stuff, make sure that you write it down in the little comment section that we have. We'll try and answer it as soon as possible. Okay, this is taking very long. It's because we're doing a lot of epochs, to be fair, 10,000 epochs. Alright, okay, I'm going to stop that, it's taking too long. Let's train it for 10 epochs. What does it look like after that? So you can see it's slowly starting to learn it. So first off, let's see what it looks like after one epoch, okay? So we went from this to the slightly closer match. Then we do 10, slightly closer. We do 100. It's almost there. But with a few more, it basically makes sure that these points go all the way to 1 and 0. And this model would already, I'm sure, perform very well if we just thresholded it at 0.5 and said, okay, anything that's above 0.5 is a 1, and anything that's below is a 0. And then it would match it almost exactly. Okay, cool. So that's binary classification. Okay, we might have, okay, so this is the case where we're just trying to predict yes or no, is this house suitable for a family or not? But we might have cases where we have categorical outputs, so there's multi-class classification. So I'm looking at an image and I'm trying to predict, is it a cat, dog, horse, mouse, whatever. So there's more than just kind of these two classes of yes or no. So the way we were doing the single node output, the way we were doing binary classification, we have this single output, which basically outputs us the probability of it being yes or no. But if we have multiple classes, okay, what we have is one node output node or output value for each class and each one of these represents the probability of it belonging to any one of those classes. Okay, so we also change our activation function depending on exactly the problem that we're trying to solve. Okay, so if our classes are mutually exclusive, and what that means is that like two classes can't be true at the same time. For example, if I'm looking at images of animals and I see a dog, like it definitely can't be a cat, right? So basically, if all the classes are mutually exclusive, meaning you can't have one image which belongs to multiple classes, then what we use is the Softmax Activation function. And Softmax Activation function, somewhat similar to the sigmoid, but basically it kind of adheres to two constraints. A, every single one of our output nodes will be between 0 and 1, so it's a probability. And B, the sum of the value of all the output nodes is equal to 1. Which makes sense, right? Because the probability of it belonging to any of these, the probability should sum to 1, because it can, because that's just how probabilities work. Okay, so that's the softmax, and I'm gonna, okay, so just to be clear, let's say we have, bring it back to this example. We have some input features about houses, and we're trying to predict categorically what era this house was from. So either it's Victorian or Georgian, let's say. We have two outputs. And because these are distinct eras, a house can't be both a Georgian house and a Victorian house, right? So what that means is that our output probabilities have to sum to 1. So this first node will represent the probability of our output, of our house being a Victorian house, let's say, and our second output will predict the probability of it being a Georgian house. Okay, hope that makes sense. If it doesn't, make sure you comment. Okay, so what now? Okay, so what this is basically saying is that so far we've been working with models where we have multiple inputs and a single output. So yeah, one way we could model this problem is of the multiple outputs is train multiple ones of these single output classifiers. So where each one of these different models, so this one will predict the probability of it being a Victorian house, this one would predict the probability of it being a Georgian house, etc., etc. What we do, and yeah, what would happen here is our x is a vector, our weights are a vector, and when we multiply those two vectors, we get a single output. But what we can do is we can kind of combine them all into one. Okay, so these three weights, become these three weights here. And what happens now, because each one of these weights is a vector, we just concatenate them and we make it into a matrix, so that when we get these three inputs and we multiply them by this matrix, we get three distinct outputs. And each output kind of has its own weights for each input. So this, and this are exactly the same, except for this is just simpler because we're just multiplying it by a single matrix. So yeah, now here, this is basically talking about the softmax function and how that works. So the softmax function takes each output, exponentiates it to turn it into a positive value, okay, and then we divide it by the sum of all the outputs exponentiated. Okay, so yeah, it's kind of self-explanatory. We exponentiate every output, and then we divide them by the sum of all of that. So yeah, each output should be within the range of 0 to 1, and it should all sum up to 1. Okay, that's basically it. And yeah, I hope that made sense. Again, if it doesn't, make sure you comment. And yeah, see you guys soon.